Okay. All right. So let's continue discussion of Jacobi fields. So if gamma is a geodesic in a Riemannian manifold M with initial conditions gamma 0 equal to P and gamma prime 0 equal to V, then the space of Jacobi fields is the space of vector fields J along gamma which satisfy the second order linear ODE J double prime plus R gamma prime J gamma prime equal to 0. And since this is a second order linear ODE, any solution is uniquely determined by its initial conditions J0 and J prime 0. So the space of Jacobi fields is identified with TPM direct sum TPM. So it has dimension 2n. And then we saw there's a direct sum decomposition of the space of Jacobi fields into the space of tangential Jacobi fields, direct sum the space of normal Jacobi fields. So here, these are the tangential Jacobi fields, and these are the normal Jacobi fields. So the tangential Jacobi fields are given by the following. You have always these two trivial solutions to the Jacobi equation. J1 of t is gamma prime t, and J2 of t is t times gamma prime t. So these, as we saw last time, these satisfy the Jacobi equation, and these are tangent to the curve, right, gamma. So the space of tangential Jacobi fields is, these two are easy to see, they're linearly independent. So the space of tangential Jacobi fields is the direct sum of the spans of these two Jacobi fields. So Rj1 direct sum Rj2. And then the space of normal Jacobi fields was the space of Jacobi fields which are everywhere perpendicular to the curve. Okay, so inner product J gamma prime is identically equal to 0. And then we saw that this is equivalent to just saying that the initial value of J0 is perpendicular to the curve at time 0. So inner product J0V is 0. And also the initial value of J prime is perpendicular to the curve. So inner product J prime 0V is 0. Okay. All right, so the tangential Jacobi fields has dimension 2, and the normal Jacobi fields, these are given by two linear equations. So this has dimension 2n minus 2, right? Is this okay? Yeah.
Yes, sir.
And so we also saw that we can use Jacobi fields to describe the derivative of the exponential map. So at any tangent vector v in the tangent space. So if I take a tangent vector at v, so say some w, okay, so then I get a curve in the tangent space. S goes to v plus sw, right? So exponentiating these vectors v and v plus sw, right? These will give me a one parameter family of geodesics. Okay, in M. So this is in TPM. And the image is in M. Okay. So this is P. And this is, say, gamma of 1, which is XPV. And then exponentiating these gives me this one parameter family of curves. Okay, so this will be gamma S of 1, okay, where gamma S of T is the geodesic with initial conditions, with initial velocity V plus SW. So this will be XP of T V plus SW, right? Okay, and when you differentiate it with respect to S here at S equal to 0, then you get a tangent vector to V in the tangent space W, and the exponential maps this to the derivative with respect to S of this one parameter family of geodesics, right? Okay. So from that, it's easy to see that basically by the chain rule, the tangent vector, when you differentiate with respect to S here, this is the value of a Jacobi field, right? J at time 1. So this tangent vector here, this is J of 1. Okay. And from the chain rule, you can see here, the tangent vector W under the derivative of the exponential goes to J of 1 here, right? So that gives us that dx p at the point V of W is J of 1, right? And here the initial conditions of J are J0, J prime 0. These, well, J0 is 0 because all of these geodesics start from P. So when I differentiate with respect to S equal to 0 at time T equal to 0, I'll get 0. And using symmetry of the connection, we found that J prime 0 is equal to W, right? Is this clear? Yeah.
Yes.
Okay, so this is what we saw last time. And as a consequence of this, we obtain what's called the Gauss lemma. So it says the following. So if I take W to be perpendicular to V here, okay, so what do I mean? So let me take the here. Oh, sorry. Sorry. So if I take W to be perpendicular to V here, then W I can think of as a tangent vector to the sphere of radius norm V, right? Yes. So if I take W to be a tangent vector at V to the sphere SR, okay. So let me put R equal to norm V. Okay, so this sphere of radius r, SR is the set of U in TPM such that norm U is equal to R. Okay, so this is the submanifold of the tangent space, and the tangent space to this sphere is identified with V perp, right? Yes.
Yes.
So that's what we have in this picture here. This W is tangent to this sphere. Okay. So if W is in V perp, what does this mean? This means that this Jacobi field J satisfies inner product J0 V. This is 0 because J0 is 0, and inner product J prime 0 V. This is inner product WV. This is also 0 because W is in V perp, right? So if J0 and J prime 0 are perpendicular to V, that means J will be a normal Jacobi field, right? So that means this J of 1 will be perpendicular to this gamma prime 1 here, right? Okay. So this means that J belongs to the space of normal Jacobi fields. So this means that inner product J1 gamma prime 1, this is 0, right? Yes?
Yes.
Yes.
What does this mean? This means that J of 1 is the image of W under the derivative of the exponential. So this means that the derivative of the exponential at the point V, right? This is perpendicular to gamma prime 1. So the derivative of the exponential applied to V perp, this is contained in gamma prime 1 perp, okay, which is a subspace of the tangent space at gamma 1. All right. Is this clear?
Yes.
Yes.
Okay. So this is the Gauss lemma. This is the Gauss lemma. Okay. So using this Gauss lemma, one can prove that the geodesics are starting from P for short time, or I mean restricted to a geodesic ball where the exponential map is a diffeomorphism. Their geodesics are length minimizing curves from P to gamma of 1, right? Okay, we can use the Gauss lemma to prove this. I won't do this, but we did this last semester, if you remember.
Yes.
Okay. And what is this gamma prime 1 at perp actually? This is nothing but the tangent space to the geodesic sphere. Okay. This is nothing but the tangent space to the geodesic sphere.
Yes.
Gamma prime 1 is like this. So all this is saying is that, I mean, first you use the Gauss lemma to show that actually the, well, what do I want to say here? So, I mean, so all this is saying is that the exponential map sends well, the Gauss lemma actually will tell us that this gamma prime 1 perp is the tangent space to the geodesic sphere. The geodesic sphere, by definition, is the image of the sphere in the tangent space. Okay. So if the exponential maps the sphere in the tangent space to the geodesic sphere, then of course it's going to map the tangent space to the sphere to the tangent space to the geodesic sphere, right? Yes.
Yes.
But what the Gauss lemma tells us is that the tangent space to the geodesic sphere is actually gamma prime 1 perp. Okay. I mean, we can use the Gauss lemma to show that. We can use the Gauss lemma to show that. Okay. So this is, yeah, so this V prime is, V perp is identified with the tangent space to the sphere in the tangent space, and the derivative of the exponential map at V maps this to the tangent space at the point gamma 1 to the geodesic sphere SPR, and this is identified with gamma prime 1. Well, this is equal to, this is not an identification, this is equal to. Okay. Okay, so this equality that the tangent space to the geodesic sphere is the orthogonal complement of the geodesic. This I mean, this follows from the Gauss lemma. See, what the Gauss lemma is telling you is that this see the image under the exponential of V perp, right? This is the image of the tangent space to the sphere in the tangents in TPM. So that's going to map to the tangent space to the geodesic sphere. Now that is contained inside gamma prime 1 perp, right? So in other words, what it's saying is that the geodesics issuing from P are perpendicular to the geodesic spheres. So that is in simplest forms, that's what the Gauss lemma is saying. That if you look at the geodesic spheres centered around P, and you look at the geodesics starting from P, then these are orthogonal. Okay. So that's what the Gauss lemma is saying. Yeah. I think that's the best way to say it. Does that make sense? Yes?
Yes, sir.
Okay. So geodesic spheres centered at P are orthogonal to geodesics starting from P. Right. So this is a generalization of what you see in Euclidean space, right? That the radii are perpendicular to a sphere, right? So in a Riemannian manifold, the radial geodesics are perpendicular to the geodesic spheres. Okay. Is that all right?
Yes, sir.
Any questions?
Sir, the last equality that you have written, that this tangent space to the sphere is equal to the gamma prime 1 part. Why is that?
Right, right. Okay. Well, look, see, okay, wait. So the exponential.
This is not equality, this is identification. Right?
No, this is actually equality, right? Both are subspaces of T gamma 1 M, right?
Okay. Yes, yes, fine. Yeah.
Both are subspaces of T gamma 1 M.
Yeah, now it's
Is this okay? Yeah.
Yes, yes,
And you understand how the equality follows from the Gauss lemma, right?
yes, yes.
That's okay. Yeah, that's all right.
That. And this DXPV is a isomorphism.
Right, because we're
The
taking
last
geodesic.
you wrote the subspace, that subspace thing, that will be a equality, right? I mean, the last implication
This is
because
an
of the
equal.
diamond.
Sorry.
No, what I'm saying is DXPPV evaluated on V per, that will be equal to gamma prime 1 P.
Yeah. Actually, this will be an equality because of equality of dimensions. Right. Correct. This has dimension n-1 and this also has dimension n-1. So actually they're equal. Yeah, that's right. Correct. That's what you're saying, right?
Yes, sir. Yes, exactly.
Okay. Yeah. Correct. Yeah. Okay. All right. So this is all I wanted to say about the Gauss lemma. So now let's carry on with the notes. So yeah. So we have this Gauss lemma. Okay. So now, so far we haven't actually computed any examples of Jacobi fields, right? So let's do that in the simplest case where M is a complete two manifold, so two-dimensional, a surface of constant sectional curvature. All right. So suppose the sectional curvature at all points is equal to a constant K. Okay. So then if we take a geodesic gamma with initial conditions P and V, and we let N be a parallel vector field along gamma, which is a parallel unit normal vector field. Okay. So N0 is perpendicular to V and norm of N0 is 1. And then I parallel transport this N0 along gamma to get a unit normal, which is parallel along gamma. Okay. So then N is everywhere perpendicular to gamma prime and norm N is constant equal to 1, right? So now let J be a normal Jacobi field. Then since N is a, so the orthogonal complement of gamma prime in two dimensions is just one dimensional. It's spanned by N. So that means J must be a multiple of N, right? So J is some function F times N, all right? Yes?
Yes.
And
Right.
since N is parallel, that means that J double prime will be F double prime into N, right? Because N is parallel.
Yes.
So now what does the Jacobi equation become? It becomes F double prime N plus F times R of gamma prime N gamma prime equal to 0, right? This is the Jacobi equation now.
Yes. Right.
So now what I do is I take the inner product with N on both sides. So then I get F double prime into N inner product N is 1. So this gives me just F double prime plus I'll get F times. So here I'll get an inner product R gamma prime N gamma prime N. This by definition, this is the sectional curvature, right? At the point gamma t of the tangent space at gamma t. Into the norm of gamma prime wedge N squared, right? By definition of sectional curvature, this inner product is equal to this, right? So the sectional curvature is constant equal to K. So this becomes K times, and this norm of gamma prime wedge N squared, this becomes norm gamma prime squared into norm N squared minus inner product gamma prime N squared. So this just becomes 1, right? Norm gamma prime 1 and norm N is 1 and inner product gamma prime N is 0. So the whole thing just becomes K. So when I take inner product with N, finally I just get a scalar ODE, second order linear ODE, right? F double prime plus KF equal to 0. Yes?
Yes.
Okay. So what do my solutions look like in that case? We know exactly what the solutions look like, right? So here we have dimension M equal to 2. And we're taking, so gamma is a geodesic. And so sectional curvature Kp sigma is equal to K for all P. Yeah. And N is a parallel normal vector field along gamma. Unit normal. Yeah. So then if I take J is a normal Jacobi field. Okay. So J is equal to some function f times n. And what we find is that f double prime plus kf equal to 0. Yeah. So then there are three cases, right? Depending on the sign of k. So case one, let me just take k equal to +1, 0, and -1, right? You can work out the other cases. So suppose k is equal to +1, right? Then what are my solutions? F is going to be alpha cos t plus beta sin t, right?
Yes.
Okay. And if J0 is equal to 0, so J0 equal to 0, these are the kind of Jacobi fields we get when looking at the differential of the exponential map, right? These correspond to geodesic variations where the initial point P is fixed, right? So if J0 is 0, then we get that this alpha must be 0, right? And so F is just a constant times sine t. Yes?
Yes.
So J is equal to constant sine t into the normal vector. Okay, so this is what our Jacobi field looks like. So this we can see. So constant curvature +1, that corresponds to the sphere S2, right? And this normal Jacobi field with J0 equal to 0, that corresponds to what? I'm taking basically, so this is my geodesic gamma. Let's say it's a longitude. Then if I rotate this longitude, right? Like this, I get a one parameter family of geodesics, right? And when I differentiate at time with respect to S equal to 0, then I'll get this Jacobi field, which looks like this, right? Yeah.
Yes.
So this, you can see this Jacobi field will be sine t times the normal vector, right? When t is 0, the Jacobi field is 0. It becomes largest when t is pi by 2. Then it's equal to the normal vector. And as t increases to pi, it again goes down to 0, right?
Yes.
Okay. So this is a concrete example of a Jacobi field here, given by rotating this geodesic, keeping the two endpoints fixed. Okay. Then we have k equal to 0. So, right. So maybe I should put here m equal to S2. So for k equal to 0, we can just take m to be R2, right? And here again, so our f double prime equal to 0 means that f is just alpha t plus beta, right? Yes?
Yes.
Okay, so if J0 is 0, then f is just alpha t. Okay, so Jt is just alpha t times n. So here Jacobi fields grow linearly, right? So here basically the picture is you start with one geodesic, it's just a straight line in R2, say passing through the origin. Then I rotate this, right? If I rotate this, and then differentiate with respect to the parameter, then I'll get this linear. Oh, this is a bad picture. Sorry. Let me just make this better. Yeah, so like I was doing here, I rotated a geodesic, keeping the starting point fixed. So again, I rotate around the starting point. So I'll get this geodesic, this Jacobi field, which grows linearly, right? You can see in the picture, the Jacobi field is growing linearly. Is this okay?
Yes.
Okay. And finally, what's the last example?
K equals to -1.
K equal to -1. So then M is equal to H2, which we can take to be the unit disk, right? Okay, so then F will be what? Alpha cos HT plus beta sin HT, right? Yes. And so if J0 is equal to 0, then F is equal to beta sin HT. And so JT is beta sin HT into N. Okay, and here again, we have the same picture. You take a geodesic through the origin of the disk and you rotate it, right? Okay, keeping rotated around the origin and then differentiate. So here you'll get a Jacobi field which grows exponentially. Okay. Is this all right?
Yes, sir.
Yeah. So actually these three examples, they're all of the form, your one parameter family of geodesics, gamma S is KS gamma 0, right? KS gamma, where KS is a one parameter subgroup in the maximal compact K, right? These are all symmetric spaces. So this is what we're doing, right? KS is the stabilizer of the, this K is the, well, this K is one dimensional in all, in this examples, in these examples, KS is equal to K, right?
Yes.
In these three examples. Is this clear? Yeah.
Yes.
Okay. So this is nothing, I mean, this is isomorphic. This is just isomorphic to S1. And this is, so, I mean, wait, so this is the stabilizer of the origin, okay, in the isometry group. And this is isomorphic to S1. Okay.
So
And
what
J
is this S?
is the one parameter subgroup of rotations,
Okay.
right? S is the angle, that's it.
Hmm.
Is this all right? Yeah.
Yes. Yes.
Okay. So maybe I should call it K theta really instead of KS. But anyway, yeah. But you usually for the family of geodesics, I use the parameter as S. Okay. Is this all right? Yeah. So, I mean, you can do this in any dimensional symmetric space. So in HN or SN or RN, you can do the same, right? There you'll take a one parameter subgroup of the maximal compact K. And you apply it to your geodesic, and then you'll get a one parameter family of geodesics. You differentiate that, you'll get a Jacobi field with J0 equal to 0, right?
Yes.
Okay. So any questions about this? So are these three pictures clear? Yeah. So, okay. So in positive curvature, you can see the norm of Jacobi fields. This is actually concave. And in non-positive curvature, where K is 0 or -1, here the norm of the Jacobi field is convex. You see, the norm of the Jacobi field is convex. So this will be true in general in higher dimensions too. Okay, so let's stop here and start a new session. Okay. Okay, so now, so we saw that looking at in the two-dimensional case, looking at the Jacobi equation for a normal Jacobi field, it just leads us to the standard second order linear OD, scalar linear OD, f double prime plus kf equal to 0, right? Where k is the curvature, the sectional curvature along the geodesic. So here I took k to be constant, but we can also think about the case of the general case of variable curvature, right? Then k will be a function of t, right? Yes?
Yes.
K will be a function of t, but then we can look at what happens if I impose, for example, bounds on the sectional curvature. So suppose I say that the sectional curvature k of t, k is less than or equal to -1 at all points in the manifold, right? So let me look at a slightly more general case, still in two dimensions. Okay. So still in two dimensions. So again, dimension m equal to 2. Now suppose Kp sigma is less than or equal to some constant k for all p and m. Okay. So then if you're given a geodesic gamma, you let k of t be the curvature at the point gamma of t. All right. So this is going to be less than or equal to k. And so then if I take J to be a normal Jacobi field, right, then what I get is that f double dash t plus kt ft, this is equal to 0, right? Now, standard classical, your classical theory of ODEs, these second order linear ODEs will tell you that if KT is less than or equal to K, then what happens to solutions of this ODE? Can you say what solutions of this ODE will look like? So let me call this ODE star. So KT less than or equal to K, this implies that solutions to star grow faster than solutions to the ODE with constant coefficients, f double dash plus kf equal to 0, okay, with the same initial conditions. So let me say the initial conditions are, say, f0 equal to 0 and f prime 0 equal to 1, let's say. Okay. Yes. Have you seen this kind of result before in your classical ODEs? Yes.
No, sir, actually.
Okay, fine. I mean, Rudroda, maybe you're familiar with such results?
Yeah, I've seen it, but
Okay.
yeah,
This is just to remind you of that we're going to prove a general comparison result for Jacobi fields. So the idea is that in a manifold of curvature bounded above by K, Jacobi fields will grow faster than Jacobi fields in a space of constant sectional curvature K. Okay, that's what we're going to show. And
not in this generality. I have not seen in this
no, but
generality.
I'm just saying that it's a generalization of this classical fact about
Yeah,
scale.
that's true. Right.
It's a generalization of a classical, very classical thing. That's all.
Right.
And trying to make the link with a very classical fact,
Right.
which is a Sturm-Liouville theory. Sturm-Liouville theory.
Hmm.
It's Sturm-Liouville theory. Yeah. So, okay. So yeah, I mean, so in a sense, Jacobi equation is sort of a generalization of Sturm-Liouville theory to higher dimensions. You can think of it like that. Yeah. Sturm-Liouville theory is scalar for scalar equations. Jacobi equation is for vector valued functions, right? So it's sort of a generalization in that sense. Okay, so let's come to this compare. So this is just to motivate what we are going to prove now, which is the comparison results for Jacobi fields. And why are we doing this? Because comparison results will give us, for example, comparison results for the volumes of balls, geodesic balls, in spaces of curvature bounded above and below. Right, what we'll find is that the volume of geodesic balls will grow, at most as fast as volumes of balls in constant curvature spaces, or at least as fast, and so on, depending on upper and lower curvature bounds. We'll get bounds on the growth of balls, volume growth of balls, and for the spaces of constant curvature, we'll be able to compute the volume growth explicitly using Jacobi fields. Okay. So that's the goal for now. All right. So let's come to that. So, okay. Okay. So before doing that, I want to say a bit more about what happens in the case of non-positive curvature. So sectional curvature less than or equal to 0. Okay. So let's do the following calculation. If J is a Jacobi field along a geodesic gamma, let's look at the function norm j squared. Okay, so if we differentiate this once, then we'll get 2 times inner product j prime j, right? Now, if I differentiate this again, then that means I'm differentiating this inner product j prime j. So by the metric compatibility, what will this be? This will be 2 times. So I'll get a j double prime j term and a j prime term, right? So this will be 2 times norm j prime squared plus inner product j double prime j. Okay. And now I use the Jacobi equation. So because j is a Jacobi field, j double prime is minus of r gamma prime j gamma prime. Okay. So this becomes 2 norm j prime squared minus r gamma prime j gamma prime inner product j. And this inner product, by definition of sectional curvature, this is the sectional curvature of the span of gamma prime and j into the norm of gamma prime wedge j squared, right? Yeah, this is by definition of sectional curvature. Okay. So this norm j prime squared is non-negative. So this whole thing is greater than or equal to minus 2 times this sectional curvature into this norm gamma prime wedge j squared. So what do we get? We get that for any Jacobi field, the second derivative of norm j squared is greater than or equal to minus 2 times a sectional curvature of the span of gamma prime and j into norm gamma prime wedge j squared. Okay. So now suppose n is non-positively curved. That means that the sectional curvature is less than or equal to 0 for all points P and for all 2-dimensional subspaces sigma in TPM. Then this equation, this K will be less than or equal to 0. Therefore, this second derivative of norm j squared will be greater than or equal to 0, right?
Yes.
Yes. So
Yes.
therefore, that means that norm j squared is then a convex function of T, right? So this is what I was saying. What we saw in the examples here for R2 and H2, this the norm of the Jacobi field here, the norm squared was, in this case, was like T squared, which is a convex function of T. And in this case, the norm squared was sin h squared T. That's also a convex function of T. So what we're seeing in general is that in non-positive curvature, the norm squared of a Jacobi field is convex. Okay. So therefore, if I have, so it's a convex non-negative function. So if it vanishes twice, let's say j of T1 is 0 and j of T2 is 0, where T1 is less than T2, then by convexity for all T in the interval from T1 to T2, we can write T as a convex combination of T1 and T2. And so then norm JT squared, this will be less than 1 minus alpha JT norm JT1 squared plus alpha norm JT2 squared, right, by convexity. And both of these are 0. So this will be 0. So therefore, norm JT will be 0 for all T in the interval T1 to T2, right?
Yes.
Okay, so if a Jacobi field in non-positive curvature, if it vanishes twice, then it vanishes everywhere in the interval in between. Okay, but if it's 0 in this interval, then J prime T is also 0 in this interval, right? But then that means in this interval, the pair JT comma J prime T is 0 for all T in this interval, right? But therefore, but these are the initial conditions, right? This JT J prime T for any T I can take these to be initial conditions for my Jacobi field. And I know by uniqueness of solutions to the Jacobi equation, this will imply that J is identically 0, right? For all T. Yes?
Yes.
If these initial conditions vanish, then J is identically 0. So therefore, we get that in non-positive curvature, if a Jacobi field vanishes twice, then it vanishes identically. Okay. Then it vanishes identically. Is this clear?
Yes.
So as a corollary, we get the following. Suppose M is complete and non-positively curved. Okay. Then the exponential map. So since M is complete, it's defined on all of TPM, the exponential map. Then the claim is the exponential map is a local diffeomorphism. Okay. So in non-positive curvature, for a complete manifold, the exponential map is a local diffeomorphism. Okay. So by the inverse function theorem, it's enough to show that the derivative of the exponential map at all points is an isomorphism, right? Okay. So we have to show the derivative of the exponential at any vector v in the tangent space. So this is going to map from where to where? From TV TPM, right, which is identified with TPM itself, to the tangent space at the point xp of v in M. This we have to show is injective, right? This linear map. Yeah. So there are two cases. If v is equal to 0, then this becomes the derivative of the exponential at the origin. This we saw is just the identity from TPM to TPM. So in this case, we're done. Otherwise, if v is non-zero, then you let gamma be the geodesic with initial conditions p, comma v. Then for any w in the tangent space at v to TPM, which you identify with TPM. So we know that dxp of v at v of w, this is equal to a Jacobi field jw of 1, right? Where jw is the unique Jacobi field with initial conditions j0 equal to 0 and j prime 0 equal to w, right?
Right.
Okay.
Yes.
So then I want to show this derivative of the exponential is 1 to 1. So I want to show its kernel is trivial. So suppose the derivative of the exponential applied to w is 0, right? Then that means that jw of 1 is 0, right? And then jw of 0 is also 0, we know. But then because M is non-positively curved, we've just seen if a Jacobi field vanishes twice, then it is identically 0, right?
Yes. Yes.
So therefore, J is identically 0. That means J prime 0 is 0, but J prime 0 is W. So therefore, W is 0, right? Is this okay?
Yes, sir.
So therefore, if the derivative of the exponential maps W to 0, then W is 0. That means this is an injective linear map, right? Is this clear? And so we're done. Okay. So the derivative of the exponential is an isomorphism everywhere. And so therefore the exponential is a local diffeomorphism by the inverse function theorem. Is this okay?
Yes.
Yes.
All right. Actually, we can prove the following, which we won't prove. I'm just going to state. The Carter and Hadamard theorem says, in fact, the following, that if M is a complete non-positively curved Riemannian manifold and P is a point in M, then in fact, the exponential map from TPM to M, this is actually a covering map. Okay. So, this is a non-trivial statement because local diffeomorphisms are not always covering maps, right? But I mean, the converse is true. Any covering map is always a local diffeomorphism, but local diffeomorphism need not always be a covering map. So here the completeness is important in this statement. Okay. So one can prove that this local diffeomorphism is in fact a covering map. Okay. And if M is simply connected, then this covering map actually has to be a homeomorphism, right? It has to be 1-to-1. Yes?
Yes.
Okay, so therefore, in the simply connected case, the exponential map is a diffeomorphism. Okay, so in particular, what does this mean? This means that if I have a complete manifold, which is simply connected, then non-positive curvature will imply that the manifold is in fact diffeomorphic to Rn, right? This tangent space is the same as Rn, right? So the manifold is diffeomorphic to Rn. So in particular, it is contractible, right? So here you see that curvature has implications for the topology of the manifold. So just simply connected together with non-positive curvature, that implies contractible, right? Okay. So, for example, this means that on the n sphere Sn, there is no metric which is non-positively curved everywhere. You cannot have a metric on Sn which is non-positively curved everywhere. Why?
Then it will be contractible.
Right, but Sn is not contractible, right? So Sn is simply connected for n at least 2. It is simply connected, but it is not contractible, right?
Yes.
So any Riemannian metric on Sn, it has to have a point where the sectional curvature is positive. Okay, there has to be a point and a two plane where the sectional curvature is positive. Okay.
Right.
So this is one example of curvature influencing topology. This is a theme in Riemannian geometry that curvature bounds have topological implications. They have topological implications. So here simply connected plus non-positive curvature and of course completeness, that implies contractible. Okay. So I should just say, thanks to this theorem, we call, this is just a useful terminology, a Hadamard manifold is exactly a manifold which satisfies the hypothesis of the Cartan Hadamard theorem. So a Hadamard manifold is equal to a complete simply connected non-positively curved manifold, Riemannian manifold. Okay. So the Cartan-Hadamard theorem says that for any Hadamard manifold, the exponential map is a diffeomorphism from the tangent space to the manifold. Okay. Okay, so examples of Hadamard manifolds are higher rank symmetric spaces of non-compact type, or any symmetric space of non-compact type, whether rank 1 or higher rank, all of them are non-positively curved. Okay. And they're complete and simply connected. And so all of them topologically are trivial. They're diffeomorphic to Rn. Okay. It's just the geometry which is different. So the topology is trivial. So, is this okay?
Yes, sir.
Okay, so let's now come to the comparison theorems for Jacobi fields. Okay, so actually, I should make a remark here. The most general comparison theorem for Jacobi fields is called the Rauch comparison theorem, but the proof of that is quite involved, so I won't do that. I'll do a simpler version for our situation. Okay, so I'll just call it a Jacobi field comparison theorem. This is good enough for our purposes. Okay. All right, so it says the following. So let M be complete, and suppose the sectional curvature, okay, and I'll only do it in the case of negatively curved manifolds, okay? So I won't talk about positive curvature, just negative curvature. So suppose the sectional curvature is less than or equal to a constant minus a squared. Okay, at all points and at all two planes sigma, and a here is some positive constant. So let gamma be a unit speed geodesic, and let J be a normal Jacobi field along gamma, such that J0 is 0 and J prime 0 is some W, which is perpendicular to V. Okay, where here the initial conditions of gamma are P and V. Okay. So then we want to say that the norm of J, it grows at least as fast as the solution to the ODE, where this upper bound on the curvature, you replace the curvature by the upper bound, okay, minus a squared. So you let f sub a be a solution to this ODE, fa double prime minus a squared fa equal to 0. All right. So this fa actually would be the norm of a Jacobi field in H in a space of constant curvature minus a squared. All right, this would be the norm of a Jacobi field in a space of constant curvature minus a squared. All right. So where fa satisfies the initial conditions, fa of 0 is 0 and fa prime 0 is positive. Okay. Then we have the following comparison results, that if fa prime 0 is equal to norm J prime 0, so this in a sense says that the Jacobi field in M has the same initial conditions as the Jacobi field in the space of constant curvature minus a squared. All right. This fa prime 0 equal to norm J prime 0, which is norm W. Then norm of JT is greater than or equal to fa of t for all t. Okay. Is this clear? Yeah. So an upper curvature bound implies that the Jacobi field grows at least as fast as the Jacobi field in the space of constant curvature minus a squared. All right. And this fa of t we can calculate explicitly, right? If we know these initial conditions, fa of 0 is 0 and fa prime 0 is norm W, then that means that fa of t is actually going to be sin h at over a into norm W. Okay, so we get that the Jacobi field grows at least as fast as this. Okay. This would be the right-hand side is the norm of the Jacobi field in H2 with constant curvature minus a squared. All right.
Yes.
Is this? Yeah, okay. So this is the first comparison theorem. And the second comparison theorem is the following, that suppose I choose this FA such that at some time capital T, FAT has the same value as norm JT. Okay. So then I get that this inner product J prime capital T JT. So this is greater than or equal to the following: A cottage AT into norm JT squared. And this you can calculate. You're given what FA of T, you can work out what FA of T has to be. This will turn out to be actually norm of JT into FA prime T. Okay, so this second statement is a bit unclear what I'm trying to say here. What is this norm J of T? This is the same as FA of T, right? So this is FA of T, FA prime T, right? So the second statement, actually what I'm saying is, let me write the second statement here. So so here is a time T. Okay, I'm taking a Jacobi field, which is 0 at 0. And then I'm taking this function FA of T, which satisfies the second order ODE with constant coefficient. Okay. So this is norm J of T. Okay. This graph here, this is the graph of norm J. Okay. And then I draw FA here. So FA is going to look like this. I'm choosing FA such that, so this is norm J and this is FA, this graph here. All right. And I'm choosing FA such that FA has the same value at time T as norm J. Okay. So FA of T is equal to norm J of T. Then what I'm saying is that inner product J of J prime T, J of T, this is greater than or equal to norm JT into FA prime T. So what is this? This is FA of T into FA prime T, right? Okay. So this side is what? If I multiply by a 2 on both sides, then this is what? This is just ddt at T equal to T of norm JT squared, right?
Yes.
And this is ddt at T equal to capital T of FA squared, right?
Yes.
And that you can see in this graph here. Basically, the point is that this norm J, this will be more convex than the curve FA. So if they have the same values at the endpoints, then the slope of norm J will be greater than the slope of FA. That's what this second inequality is saying. Is it clear now?
Yes.
Okay. This slope is bigger than this slope. All right. So is this okay? Yeah. Okay. Okay. So let's try and prove this now.
Oh,
Oh yes, any remark or comment?
no.
Is the picture clear?
So from T, the J is growing faster. That's what we are saying.
Yeah, so I'm saying that basically, I'm choosing this FA such that it has the same value at the endpoints of this interval 0 to T, right?
Hmm.
Then the idea is that norm J should be more convex than FA. As you can see here, it should lie below FA, right?
Right.
It should be
Yes.
the inequality on sectional curvature will make the Jacobi field more convex than the Jacobi field in constant curvature. That's the idea. The more negative the sectional curvature is, the more convex the Jacobi field becomes.
Yes. Right.
Okay. So in this picture, if you have a picture like this, then the slope of the lower curve is bigger than the slope of this curve, right? Over here.
Yes.
So that's what this inequality is saying, right? This slope is bigger than this slope. Okay. Does it make sense? Yeah. Okay. Orkojit, is that all
So,
right?
but norm of JT should be above FA, right? I mean, from theorem, the part 1.
No. What I mean is, see, maybe the notation is a bit confusing. So see, I'm choosing FA in two different ways in part 1 and part 2. Like these are not the same FA. These are not the same FA. So if FA satisfies this condition, then I have this inequality. And if FA satisfies this condition, then I have this inequality.
Okay.
So these are two different FAs. They're not the same function FA.
Okay.
Do you understand?
Yes, fine.
Now it makes sense, yeah? It's
yes.
So I can choose FA which as I please. I can choose FA to suit my what I want to prove. Okay, so yeah, so it's not the same function FA in part 1 and 2. It's two different functions, yeah. Okay, so I mean in part 1 maybe the picture is different. Okay, then part 1 the picture is basically I have my two convex functions. So maybe I should write this is what the picture for part 2, and the picture for part 1 is that the picture for part 1 is that they have the same slope at time. They have the same slope at time 0.
Yes.
Okay, so FA will look like this and norm J will look like this. Okay, this will be FA and this will be norm J. Okay, they have the same slope at time 0. Now, does it make sense?
Yes.
So these are two different choices of FA, you see? These are two different choices of FA. Okay.
Yes. Once we are commenting about the derivative and for the first one, we commented about the magnitude and next one is about the derivative.
Yeah, I mean, the first one, look, FA, in the first one, I choose FA so that it has the same slope as norm J at time 0. And in the second one, I'm choosing FA so that it has the same values as norm J at the endpoints of a given interval, 0 to capital T. All right. So if I draw them on the same graph, then I'll get two different FAs. One FA looks like this, the other FA will look like this with the same slope here. You see, these are not the same FA. These are two different FAs. Now, does it make sense?
Yes, fine.
Okay. Yeah, sorry, the notation is a bit confusing. It seems like it's the same function. It's not the same function. Okay. All right. So, okay, let's come to the proof. It's not very difficult. It's just some simple calculus. So, okay. So J0 is given to be 0 and J prime 0 is some W, which is we're assuming is non-zero. So, then by what we proved in non-positive curvature, So here we're assuming the sectional curvature is negative. So therefore, J can only vanish once, right? So therefore, if J0 is 0, then JT is non-zero for all T non-zero, right? Okay. Because in non-positive curvature, a non-zero Jacobi field can only vanish once, right?
Yes.
It vanishes
Right.
identically. Okay, so JT is non-zero for all T non-zero. And so therefore, if we look at the function f of T, which is norm of JT, this is smooth outside the origin, okay? Yeah, this is smooth outside the origin. So let's differentiate for T positive, we can differentiate. So F prime T will be what? This is inner product JJ to the power half. So F prime T will be half of inner product JJ to the minus half into 2 inner product J. Okay. All right. So we're proving this Jacobi field comparison theorem. So we're looking at the function f of t is the norm of j of t. So this is smooth outside the origin. So let's differentiate for t positive. So the first derivative f prime t, we find this is equal to inner product j prime j into norm j to the power minus 1, right? Okay. So now let's look at the second derivative. So f double dash t will be what? So by the product rule, I have to differentiate this j prime j. So this derivative we already computed, right? This is going to be norm j prime squared minus sectional curvature k of gamma prime j into, well, norm of gamma prime wedge j squared, but j is a normal Jacobi field. So, and gamma is a unit speed geodesic. So norm of gamma prime wedge j squared will just be equal to norm j squared, right? Is that okay?
Yes.
Yes.
So we'll get this term, this into norm j inverse, plus I have inner product j prime j into the derivative of norm j inverse. So by the chain rule, that's minus norm j to the minus 2 into the derivative of norm j, which we've already calculated. That is inner product j prime j into norm j inverse. Okay. All right, I've written below here. Note that norm of gamma prime wedge j squared is equal to norm j squared because j is a normal Jacobi field. Okay. So j inner product gamma prime is 0. All right. So now what do I do here? So this term I take out here, this minus k gamma prime j norm j squared into norm j inverse will give me a term minus k gamma prime j norm j plus what do I have here? The remaining terms, I take a norm j to the minus 3 common. Okay. So I have a norm j inverse here. I have to take another norm j to the minus 2 out. So I have to multiply this by norm j squared, right? So I'll get norm j squared into norm j prime squared minus, here I'll get inner product j prime j into inner product j prime j. So I'll get norm j squared, norm j prime squared minus inner product j prime j whole squared. Is this clear?
Yes.
Yes.
Okay. And this by Cauchy-Schwarz inequality, this is non-negative, right? By Cauchy-Schwarz, this is non-negative. And this term here, k is less than or equal to minus a squared. So minus k will be greater than or equal to a squared, right? So this is therefore greater than or equal to a squared into norm j is again f. So finally what I get is that f double dashed is greater than or equal to a squared f. Okay. So this function norm j, this satisfies a differential inequality. f double dashed greater than or equal to a squared f. Okay. Is that clear?
Yes.
Okay. Whereas our function fa is a solution of a differential equation. It satisfies a differential equation f double dashed minus a squared f equal to 0, whereas our this function f satisfies the differential inequality f double dash minus a squared f greater than or equal to 0. Is this clear? Yeah.
Yes.
So now let's look at the following function f dashed into fa minus f into fa dashed. Okay. And I look at the derivative of this. Okay, so by the product rule, what will I get? F double dashed into fa plus f dashed fa dashed minus f dashed fa dashed minus f fa double dashed. Okay. And now fa double dashed is equal to a squared fa. So so that will give me an f double dashed minus a squared f into fa, right? And these two terms will cancel. F dashed fa dashed minus f dashed fa dashed. These two will cancel. So finally, what will I get? F double dash minus a squared f into fa, right?
Yes.
And remember, our initial condition on fa was that fa of 0 is 0 and fa dashed 0 is positive. And fa satisfies this differential equation. So these initial conditions will imply that fa is positive for t positive, right? Okay. So therefore, this whole quantity and this f double dash minus a squared f, this we've shown is greater than or equal to 0. Therefore, this product is greater than or equal to 0. All right. Yeah. So what do we get? That means that this function f dashed into fa minus f into fa dashed, this is increasing on the interval 0 infinity for any solution fa of the differential equation fa double prime minus a squared fa equal to 0. This is true for any solution, right? Which satisfies fa of 0 equal to 0 and fa dash 0 positive. Okay. All right.
Yes, sir.
Okay. Now fa of 0 is 0 and f of 0 is 0. So what I want to say is that actually the limit as t tends to 0 of this function f dashed into fa minus f into fa dashed, this is 0. So I want to justify this. The only thing I have to be careful about in this limit is that f dashed may not be bounded near 0, right? Because I only know that f is smooth outside the origin. So f dashed is smooth outside, is continuous outside the origin, but it may have a singularity near the origin, right? So I have to take care of the modulus of f dash t first. Okay, so let's do that. So mod f dash t is what? This is mod of j dash t into inner product jt into norm jt inverse. So by Cauchy-Schwarz, this is less than or equal to norm j prime into norm j inverse. So this is equal to norm j prime t. So that means that norm mod of f dashed is less than or equal to norm j dashed, and j is a smooth Jacobi field everywhere. So this is bounded as t tends to 0. Okay. So therefore, f dashed is bounded as t tends to 0. Is this all right?
Yes, sir.
Therefore, this limit f dashed into fa minus f into fa dashed, this limit is 0 because fa of 0 is 0 and f of 0 is 0. Okay. So this function tends to 0 as t tends to 0, and its derivative is greater than or equal to 0 on the interval 0 infinity. Therefore, this function is greater than or equal to 0 for all t. Is this clear?
Yes, sir.
Okay. And what is this function actually? If I divide by fa squared, then this is nothing but the derivative of f over fa, right?
Yes.
Yes.
By the quotient rule, if I divide by fa squared, this becomes the derivative of f over fa. So what do we get? We get that ddt of f over fa, this is greater than or equal to 0 for all t positive. Okay, so this is the main thing we wanted to prove. And now we can prove the two statements that we had, all right? So first, suppose that fa is chosen such that fa dash 0 is equal to norm j prime 0 is equal to norm w, okay? So if fa dash 0 is norm w, then from this initial condition, we can solve for fa explicitly. So fa of t is sin h at over a into norm w, okay? So now let's look at the ratio f over fa, okay? So I want to look at the limit of this as t tends to 0, right? So both of these vanish at t equal to 0. So I can apply L'Hopital's rule, right? So this will be limit t tends to 0. Right. Yeah, in fact, both these vanish and also the derivatives vanish at t equal to 0, right? If I take the square, because I'll get 2f into f dashed, and f vanishes at 0 and f dashed is bounded near 0. And similarly, I'll get 2 fa into fa dashed, and fa of 0 is 0, fa dashed is bounded near 0. So both of these, their derivatives also vanish at 0, right? The limit as t tends to 0 of the derivatives is also 0. So I can apply L'Hopital's rule twice, all right? Okay. Yes?
Yes.
Yes.
So this becomes the limit t tends to 0 of d squared dt squared norm j squared divided by d squared dt squared fa squared. And now I already know what these derivatives are. The second derivative of norm j squared we've calculated before. This is minus k of gamma prime j norm j squared plus norm j prime whole squared into 2 divided by this d squared dt squared of fa squared. This is just a calculation. This is a squared cos h squared at plus a squared sin h squared at into 2 into norm w squared over a squared. Okay. So now as t tends to 0, what happens? So this this sectional curvature term, this is bounded near for t near 0, and j of 0 is 0. So this term disappears. This norm j prime squared, this converges to norm j prime 0 squared. Okay. And the 2 cancel here. So on top, I get norm j prime 0 squared. And below, what happens? This cos h squared will give me an a squared. And this sin h squared will vanish. The 2 has cancelled. So the a squared will cancel with the a squared below. And I'll just get norm w squared. So finally, I'll get norm j prime 0 squared divided by norm w squared. And this is equal to 1, right? Because j prime 0 is equal to w. Okay.
Yes.
So therefore, we get that the limit of ft over f of fat, this is equal to 1. And ddt of f over fa, this is greater than or equal to 0 on 0 infinity. Therefore, this means that the function f over fa is greater than or equal to 1 on all of 0 infinity, right?
Yes.
So that means basically that ft is greater than or equal to fa of t, right? Okay, this is what we wanted to show. Yeah. So therefore, norm J of t is greater than or equal to sine h a t over a into norm w for all t. Okay. Is this clear?
Yes, sir.
Okay. So this last inequality, this doesn't mention any FA or whatever. This is just an estimate for Jacobi fields in a manifold of sectional curvature bounded above by minus a squared, right? This estimate holds for normal Jacobi fields in a manifold of sectional curvature bounded above by minus a squared. Okay, where this W is J prime 0 and J of 0 is 0. Is this okay? So we have this estimate for Jacobi fields. Okay. All right. Now we choose our FA in the second way. We choose it to agree with norm J at the endpoints of the interval 0 and capital T. Okay. So now we're choosing FA. So this is a different function FA. All right. So FA of capital T is norm J of capital T. So FA of 0 is 0. So that means FA has to be of the form some constant C times sine h at, right? Yes?
Yes, sir.
So we can solve for this constant C from this equality, right? Then C has to be what? C has to be norm JT divided by sine h at, right?
Right. Yes.
Okay. And now we use this, right, this inequality star f dashed into FA minus f into FA dashed greater than or equal to 0. So we just apply that here. So f dashed into FA, what is this? F dashed is inner product J prime J divided by norm J. This we calculated already. And FA of T is just norm J, right? And so this is greater than or equal to F into FA dashed, right? And so now I just substitute things here. So this norm J and the norm J cancel. So this gives me inner product J dash J at capital T is greater than or equal to, so F of T, that's norm JT into FA dash T. So FA dash T is going to be this norm JT divided by sine h at into A cos h at, right? If this is FA, then this is FA dashed. And so finally, what do I get? I get that inner product J prime J is greater than or equal to A cot h at into norm JT squared. Is this okay?
Yes.
Okay, so again, we get an inequality which doesn't have any auxiliary function FA. This is just about the Jacobi field J itself, that this function inner product J prime J, it has to grow at least as fast as this, okay? It has to grow at least this fast, okay? Is this all right?
Yes, sir.
Okay. So now let's continue. So we've proved these two inequalities about Jacobi fields where the sectional curvature was bounded above. Actually, we can also prove similar results when the sectional curvature is bounded below. So if the sectional curvature is bounded below by some constant minus b squared, then for any normal Jacobi field J with J0 equal to 0 and J prime 0 equal to W, we get the same sort of inequalities, but with the inequalities in the opposite direction. So in this case, you get an upper bound on norm J, this is less than or equal to sin H BT over B into norm W. Okay. And similarly, inner product J prime J is less than or equal to B cot H BT into norm J squared. Okay.
Yes, yes.
So in case of pinched negative curvature spaces, we get the both side estimates.
Exactly, exactly. So, so let me just write that down. So, if we have pinched, so what we're going to be looking at is manifolds with pinched negative curvature. So that means minus B squared less than or equal to sectional curvature K less than or equal to minus A squared. Okay. Then what we get is for Jacobi fields. So J is a normal Jacobi field with J0 equal to 0 and J prime 0 equal to W, which is perpendicular to gamma prime 0. Then we get that one norm JT, this is greater than or equal to sin H AT by A norm W and less than or equal to sin H BT by B norm W. Okay. And 2, if I look at DDT of half norm J squared, right? So this is equal to inner product of J prime with J, right? So that's what I've got estimates on. So this is greater than or equal to A cot H AT into norm JT squared and less than or equal to B cot H BT into norm JT squared. Is this okay?
Yes, sir.
Right.
So, like here, whatever we are doing is in terms of the Jacobi fields, but I just wanted to ask, like, in case of like other interesting classes of functions, say for heat kernel or something, we will get some Bosseri decay estimates or like this. And
What other function? Sorry, what are you saying?
say for heat kernel of the corresponding manifold and its decay.
Heat kernel. Right. Yeah, of course. For heat kernel, you will get other estimates. Yeah.
Are like similar to like this, like with the curvature spaces, we look at the corresponding hyperbolic space, and there we have nice growth and decay conditions. Then we can just squeeze those estimates here. Similar things. Okay.
I don't know. I think what you're saying should be true. I'll have to look it up. For the heat kernel, I'm not sure.
Okay, sorry.
Yeah. That's a whole subject in itself, the heat kernel. Estimates on the heat kernel is a big subject. So
Yeah.
I'll have to, yeah, it's a big subject. Yeah. I'll look it up and let you know.
Sure.
Yeah. Actually, see, for the heat kernel, normally you won't get two-sided bounds. Two-sided bounds are lower bounds are very difficult. You'll get upper bounds. You won't get lower bounds so easily.
Yeah, sorry. I mean See, we have a lower bound on the curvature, and then we get some, because interpreter will be interested in like long time behavior or decay. So we can get something on the right hand side. That decay would dominate this as the decay on the heat coming on our number.
Yeah. So look, I can tell you something. So this is in. If you look at, there's a paper of mine about Sullivan's construction of eigenfunctions using Brownian motion. There I've listed some standard estimates on the heat kernel, which are used in the construction of eigenfunctions. So yeah, I mean, if you look at that paper, there you'll see that if the sectional curvature, what I remember roughly, okay, if the sectional curvature is bounded above, that's the case we look at normally. If k is less than or equal to minus a squared, then I'll write it as pt of xy. Okay, this is the heat kernel. Yeah. This is less than or equal to. So, okay, so there's some polynomial part. Okay, there's a polynomial part in T. I don't remember the exact form. I'll have to look it up. Okay, and then there's an exponential term. All right. So in the exponential, there's a Gaussian part. Okay, so minus, the distance squared divided by whatever.
There's some radial function of Gaussian type.
Yeah, there's some Gaussian term, right? So look, I'm writing something very, it's going to be inaccurate. Okay, just roughly, I'm just writing it roughly. Okay. Okay, something like this you'll get, and this upper curvature bound, this gives you an extra exponential decay, e to the minus e to the minus lambda 1t. There's an extra exponential decay e to the minus lambda 1t, where lambda 1 is the supremum of the spectrum of the Laplacian.
Right.
It's the bottom value.
Right.
Okay, so spectrum of the Laplacian is minus infinity to minus lambda 1.
Right.
Okay. So yeah, so you get this extra exponential decay here, e to the minus lambda 1t.
Okay.
Yeah.
Yeah. Okay.
So this is very rough. If you want the exact formula, you can look in my paper. It's given there.
Yes.
And also the references are given there where you can find this formula.
Okay.
Okay. Yeah, but the study of the heat kernel is quite different. I mean, I don't know how these estimates are proved. I don't know really. So yeah, it's a different subject. Yeah. So,
Okay. And also, like in that paper only, there was also another statement, if I recall correctly, that if there is a lower bound on the curvature, then this may not be unique, the heat kernel. That also sounds very fascinating.
oh, really?
Maybe something. But if it's not like bounded below, then there might not be uniqueness. So yeah.
Oh, I'm not sure. Okay, I don't know this statement. Okay, I don't know.
It was in your paper.
So it's in my paper.
Yeah.
Oh, okay, well, I don't remember this.
Okay.
Okay. I don't, yeah, okay. I don't remember this. Yeah. Oh, okay, I don't remember this. Yeah. Okay. Anyway, so we have these for Jacobi fields, we have these two-sided bounds. Okay. So we've proved the lower bounds. I'm not going to prove these upper bounds. Okay. Fine. Actually, the proof of these is a little more difficult than the proof of the upper bounds. Yeah, it's so, but these are also true. Okay, so to finish, let me just briefly just talk a bit about volume on Riemannian manifolds and the volume form. So suppose M is an oriented Riemannian manifold, okay, of dimension n. Okay. So then for any point P, the tangent space TPM is an oriented inner product space. And so therefore it has a volume element, dvol P, right, which is an n form on the tangent space, such that it takes the value 1 on any positively oriented orthonormal basis, right, EI of TPM. Yeah, this is just linear algebra. We saw this in the beginning, right?
Yes.
Okay. So the volume form of the manifold M is defined to be the n form dvol. So this is an n form on the manifold, which is P goes to dvol at P. Okay. So the first thing to check is that actually this n form is a smooth n form, right? So for that, we need to look at it in local coordinates. So what does this look like in local coordinates? Okay. So suppose phi is a chart with components x1 to xn, and suppose it's an orientation preserving chart. Okay. So then dvol I can write as some function h into dx1 wedge dxn, right? And so let EI be a positively oriented orthonormal basis of TPM. Okay. Then this H of P I can write as H of P into dx1 wedge dxn applied to del del x1 del del xn, right? This last term is just 1. This is just 1, right? Okay. But now this H of P into dx1 wedge dxn, this I can write as dvol P applied to del del x1 to del del xn, right? And so let T be the unique linear map from the tangent space to itself, which sends the orthonormal basis EI to the basis del del xi. Okay. So then this I can write as dvol P of TE1 up to TEN, right? And this is nothing but T star dvol of E1 to En, right? This is the pullback by the linear map T of dvol. And we know what the pullback acting on top degree forms is. It just multiplies by the determinant, right? So this is going to be determinant T into dvol P of E1 to En, right? And dvol P of E1 to En is 1, right? So this just becomes determinant T. So this function H is nothing but the determinant of the linear map which sends a positively oriented orthonormal basis to the basis del del xi. Okay. Now we can calculate this using the metric as follows. So let G be the matrix of the Riemannian metric. So remember the components Gij are nothing but inner product del del xi del del xj, right? Okay. So what is Gij? Well, this is inner product del del xi del del xj, and del del xi is T of EI. So this is inner product TEI TEJ. So this is inner product T star TEI EJ, right? Okay.
Yes.
So in other words, this Gij, this is the matrix of T star T with respect to the orthonormal basis EI, right? Is this clear?
Yes.
This is the ijth component, right, of the matrix of T star T, right? Yes, because this is an orthonormal basis. So this is the ijth component with respect to this orthonormal basis. Okay. So therefore, what is the determinant of G? It's the determinant of T star T, right? And the determinant of T star T is the determinant of T whole squared, right? So therefore, the determinant of T is the square root of the determinant of G. Okay. So therefore, we found that our coefficient H was the determinant of T, and the determinant of T is the square root of the determinant of G. So finally, we get this formula for the volume form that dvol is equal to square root of determinant G into dx1 wedge dxn, where G is the matrix of the Riemannian metric. Okay, so this determinant G is a is a smooth function, and so is its square root. So therefore, dvol is a smooth form. Is this okay?
Yes, sir.
Okay, so this is the standard formula for the volume form of a Riemannian manifold. All right. And so we can define for any open set, we can define its volume to be the integral of this form dvol over U. And this defines a Borel measure on M, which we also denote by dvol. Okay, so we have a volume measure on any Riemannian manifold. Okay. So, yeah, there's just 3 minutes left. So let me not rush it. Any questions now? Questions, comments?
Sir, why is that upper bound proof difficult? And the other side.
Oh, why is the upper bound? Yeah, that's a good question. Okay, so yeah, okay. Why is this upper bound, right? Yeah, the
Yes.
problem is the following. You see, the problem is in the calculation of this f double dashed. Yeah. So here we have a term norm j prime squared, right? So this we are ignoring here. We're saying this is greater than or what are we saying? Yeah. Well, no, we're using Cauchy-Schwarz here to say this is greater than or equal to 0, right? Yeah. Yes.
Yes.
Okay, Orkojit, we're using Cauchy-Schwarz to say this is greater
Yes,
than or
yes, yes, right.
okay, so that gives us a differential inequality f double dash greater than or equal to a squared f when the sectional curvature is bounded above by minus a squared, right? Now, if the sectional curvature is bounded below by minus b squared, then we can say that this term minus k into norm j, this will be less than or equal to b squared f, right?
Right.
This will be less than or equal to b squared f, but this term we can't control, right?
Right.
We don't have an upper bound on this term.
Mhm.
So it becomes more complicated. Yeah, that's why. Do you understand?
Yes, yes, fine.
So that's all. It's just because of this term.
Mhm.
If you could control this term, then the rest of the proof is the same. You
Same.
just reverse the inequalities.
Mhm.
And it's the same proof. Yeah, that's so. So the problem is this term here.
Okay.
So, yeah. But the upper bound is still true. What I've written is true. For that, you have to use the Rausch comparison theorem. So that's in Tokarmo in chapter 9 or 10. You have the Rausch comparison theorem. But if you look at it, I mean, the proof is a bit long. That's why I didn't do it. So it's a bit of a long proof. Yeah. So I left it. That's all. Okay, so let's stop today and we'll continue tomorrow. Okay. So, all right. So see you tomorrow.